So what I'm going to do is I'm going to be focusing in on what exactly, or how exactly, to be a bit more precise, how do we compute one of these? So in algorithm design, very often what we'd like to do is come up and try to characterize the problem based on some special property it has that tells us how to compute what we're seeking. So in this case, I would like to know something about what a minimum spanning tree looks like in such a graph, in a weighted, let me throw that in there too, a connected, weighted, undirected graph. There's a lot of prefixes here, okay? So what I want to do is talk about how we could characterize such a thing. Now all of this has to problem. So this isn't going to be some magic thing where every time you have a problem, there's some way of characterizing it so that there's a nice, easy way to tell me how to build the answer. That isn't going to be true for every problem. In fact, there's some problems out there that don't even have algorithms that solve them. This case, we're going to have a really nice characterization for how we can obtain a minimum spanning tree. In particular, it's going to give us the key ingredient for how to find an edge in a minimum spanning tree. So the way I'm going to characterize this is by giving you something we're going to call the cut property. And we're going to prove this property, and I'm going to give you a couple of applications of how you can develop algorithms using this cut property, okay? So I'm going to state it as a theorem. So a theorem, so it's going to be called the cut property. You're going to see why I call it that, or why it's called that. And I must stress it's going to be a little bit wordy, so please bear with me, okay? So consider any weighted, and I must stress whenever I talk about the graphs in this context, it's always an undirected, simple graph. So consider any weighted connected graph G is equal to V, where V1 and V2, these are two subscripts, are two non-empty sets containing the vertices of V. So it means all the vertices, they're going to be in V1 or V2 with no common vertices. Now, for those that are acquainted with set theory, what I've described to you is that V1 and V2, these two disjoint sets, they have no elements in common. These two sets partition the set of vertices, V. That means that all the vertices are going to be in one of these two buckets, V1 or V2, but it can't be in both. So for example, V1 could be, say, these vertices here, A, B, and F. And V2 can consist of D, E, and C. Notice I've included every vertex in one of the two buckets. Now, let edge E, whose endpoints are going to be U and V, be some edge in G with least weight, where U is in V1, so it's one of the ones in this first like in the first set, the first bucket, in V1, and V is in V2. Here's the big thing that this cut property is all about. It says that there is a minimum spanning tree T that contains E. So do you notice that in my instance here, I have exactly one minimum spanning tree. There's only one possible one here. Now, I want to show you how this cut property could be used after we go through the proof, but I just want to give you an example of what I mean by this. So here's an example. I gave you V1 is A, B, and F. V2 is D, E, and C. What the cut property is saying is if you give me a least weight edge, so an edge with the smallest possible weight among those where U is one of these vertices, the ones in V1, and V is the other endpoint of the edge that's sitting outside of it. We call these cut edges. These cross the cut. So that's where the name comes from. So, for example, let me show you what these edges, which edges these are. So there's one edge right here, right? There's that edge. There's this edge. There's this edge. And there's this edge, right? So I think I got all the edges. So those are all the edges for which there is. So it's that one of the endpoints is in V1, the other one's in V2. So those are all the possible what we call cut edges. So what this cut property says is if you pick the one with least weight, so notice this one has weight 1, that has weight 1, that has weight 1, this one has weight 1. This example is not terribly interesting, but the point is notice every single one of them, doesn't matter which one it is, if I pick the one with least weight, it's in some minimum spanning tree, right? So, for example, notice that this one has least weight. Notice it's a part of the minimum spanning tree. So that's what the cut property says. It doesn't say that all the cut edges are. This is just one example where all the cut edges are part of a minimum spanning tree. But it's not all of them always. This is just an example where any one of these could be edge E in this statement. So this is very often the key ingredient for developing and discovering or designing algorithms for the minimum spanning tree problem. So let's prove this cut property. So here we go. So let's write out a proof. Now, you might ask, Dan, what exactly is the game plan here? Because I always like to go into a game plan about what exactly we're going to try to do. So I want to give you a flavor for this first before we get too into all of this. So the first thing is I want you to think in the recesses of your mind about trees, properties that trees have. Remember, a spanning tree is a tree, right? It means that there's a lot of equivalent definitions for a tree. Likewise, they have properties for which that are very helpful for us. For example, if I add an edge into a tree, then it creates at least one cycle, right? Likewise, if I remove an edge from a tree, it creates two new connected components. So these are two examples of properties that are going to be very helpful for us for proving this claim. So what I'm going to do is I'm going to start off by just simply saying, hey, look, I'm going to start off with a minimum spanning tree. Then what I'm going to do is I'm going to show you that the edge E that I have in the cut property statement has to be in this tree. So if I presume that I have a minimum spanning tree, I'm going to show you that by including E, I still end up with a minimum spanning tree. So it doesn't matter if I presume it is a minimum spanning tree, and the resulting one will have edge E in it. Okay, so I'm going to give you a recipe for how to create a minimum spanning tree given the fact that you know one exists. So if you have one, I'm going to show you how you can put edge E in as per this statement. So let T be a minimum spanning tree of G. So we're going to start off. So T is going to be a minimum spanning tree. Now remember, it is a tree, right? So by the equivalent definitions of a tree, so I'm going to use the fact it's a tree. I'm going to use one of the two properties I just talked about. Because remember, if T has E in it, we're done, right? We don't have to do anything. However, if it doesn't, as we need to really show here, if T does not contain E, then its addition to T creates what? What does it create? What does it create? It creates a cycle, right? We've added one new edge into a tree. It's connected, so we're going to add in one more edge. It's going to create at least one cycle. Creates a cycle C. So now we have a cycle. So I'm going to give this new modified graph that I've just created a name. Let now T prime be T plus edge E. Now remember, T was a spanning tree, right? Because it's an MST, right? So T was a spanning tree. Then its addition I got something more interesting to say here. Let's do that. So I'm going to draw a little picture over here to give us some intuition what's going on here. So remember, I have a cycle. So I'm going to draw us a little picture to help us kind of get an intuition around what's going on here. So anyways, imagine I have just my graph. I've got something going on with this graph. I don't know. It doesn't really matter a whole lot what's going on here. This is just some part of the graph. And this is another part of the graph. The point I'm getting at is just some part of the graph. It doesn't really matter what I'm drawing inside of here. Now, there's going to be vertices. There's going to be vertices. The vertices in this part of the graph are in V1. And the vertices in this part of the graph, including this one here, are in V2. Now remember, edge E, by definition, looks like this, right? So this is E right here. So I've included edge E into my MST, right? Now remember, this is just an edge in the graph. Now remember, it is a spanning tree, right? So there had to have been some way of getting it so that U and V are indeed a part of the spanning tree, right? So there had to be some way to get to them, right? So naturally, there's going to be some other edges. Now, I must stress that it's very easy to look at this picture and say, Dan, what the heck is going on? Why are there all these other things going on? Remember, I'm going to focus in on the edges that cross this cut. Remember, notice this is a cut, as we talked about earlier. So these edges here, suppose that these are edges in the minimum spanning tree. Suppose that these are in the minimum spanning tree. Because of the way we've constructed this right here, there had to have been some path Because remember, a tree has unique paths that go from one vertex to another, right? So that means that there has to be a path from U to V, but not using E in T. So that means that there's going to be some pathway that gets me back here. Then when I put edge E in, then I get a cycle. That's my cycle C. What my claim is that there's this edge that's a part of the minimum spanning tree. Suppose that's F. I'm going to give that a name. And let's see what happens now. So remember, the big thing you need to remember is that edge E has least weight across this cut. All these are cut edges, right? So let's talk about this. So T was a spanning tree, right? So T was a spanning tree. So in T prime, remember that's what we got over there, that weird concoction where we've added E in and we got a cycle now. So in T prime, there is some edge F, which is going to have endpoints U prime, V prime, along cycle C, where it also has one endpoint in V1 and the other in V2. Now remember, because E has least weight, right? Since E has least weight, what can we say about E and F for their weight? What can I say? Well, remember, E is not equal to F. They're not the same edge. These are two different edges. What can I say about the weight of E versus the weight of F? Almost certainly F's weight can't be less than E's because it's the least weight edge across this cut, right? So we know F is not equal to E, but that means that the weight of edge E is no more than the weight of F. So the weight of E is less than or equal to the weight of F. Now, here's the neat part, because it is we originally had a spanning tree, right? And now, if I were to get rid of F, this would break the cycle. If one removes edge F from T prime, then T prime is a spanning tree. The spanning tree and its total weight is no more than with T. So the total cost doesn't, it's either gotten better or it's the same, right? So just remember, the reason why when I remove F, so this is the primary reason, is that, remember how I said earlier that if you take an edge, because remember, T was a spanning tree, right? So when I remove this edge, it breaks the tree into two smaller trees, right? But now I have this edge E that bridges the pathway that would have otherwise not existed in T. So now I still have a spanning tree as opposed to two smaller trees. So that's why. So let's see here. So what does this mean then? It means that we still have a minimum spanning tree. Is that fun? That's pretty exciting. So why? Because T was a minimum spanning tree. Therefore, sorry, it's sort of melting. Therefore, the resulting tree T prime is also a minimum spanning tree. And that completes the proof. So notice that all I did was I showed you the recipe for how to make a minimum spanning tree with the edge E in it. So you might ask, Dan, well, how exactly do we use this cut property to come up with algorithms to solve the minimum spanning tree problem? Let's talk about that. So remember, the cut property states that if I take and I partition the vertices into two disjoint sets, V1 and V2, that means that V1 and V2 are like two buckets. I put all the vertices into two buckets. So what it's saying is, if I pick off an edge where one of the endpoints is in V1 and the other one is at V2, what I'm saying is it's such an edge with least weight, it has to be a part of some minimum spanning tree. So this gives us a recipe for how we can pick our edges such that we end up with a minimum spanning tree. That's at least how we would like to use it. So I'm going to mention you a couple of different ways we can do this. So one way we could do this, and I'm going to this one I usually spend more time talking about. I may in another video, or in another lesson I may talk about this, is that one very natural way to do this is you start off by putting, just look at our example here. Suppose that you have, and I must stress, remember, we can't just use one example to prove the correctness of an algorithm, as we previously discussed. So suppose that I start off with V1 being one of the vertices. And then everything else is in V2. What does the cut property tell us? It tells us if we find the least weight edge that crosses this cut, that it is a minimum spanning tree. It's part of some minimum spanning tree, right? It extends it into another one. So for example, notice that this is a least weight edge. So what I can do is I can extend and grow the tree from this one seed. I like to think of it like a seed. And I end up with this edge. And we know that's a part of some minimum spanning tree, right? We could continue this process. But notice that I'm growing V1 by consuming more and more of the graph, like a blob. I like to think of it like a blob that starts off over at the source or start vertex, and I must stress it doesn't matter which one you start at. The same principle applies of the cut property, right? The cut is always it's always the edges that go from V1 to V2, and we always pick the least weight edge that comes from V1 to V2. And that is always going to be closest to the blob, which happens to be consuming all of the vertices that we have so far, right? So it's closest to the blob. So notice which one of these vertices is closest to this blob? Well, it's E, right? Just one right there. So it's like 1 versus 10 versus, let's see, we've got a 3 there. But keep in mind, we might have to have some mechanism to keep track of which ones are the smallest values for how close they are to the blob. And this idea, you can keep repeatedly doing this. I'll encourage you to do that. This is one way of applying the cut property, and this gives you what we call Prim's algorithm, or the algorithm of prim-jarnik. So this is how you get Prim's algorithm. You start off with an initial seed, and you grow a minimum spanning tree from that seed by always picking a least weight edge that crosses the cut from V1 to V2, where you start off with V1 at one vertex. And when you're done this process, then you have a minimum spanning tree, because by definition, you've always picked the least weight edge every single time, and you can just keep using this over and over again. It's a very natural application of the cut property. So the Prim's algorithm is just simply where you grow a minimum spanning tree from a seed. So the way the cut works here is that you always pick the least weight edge from one side of this cut to the other, or from inside the blob to the outside of the blob. Think of it as picking the closest vertex to the blob. That blob is just really hungry, man. Now, there's another way we can use this cut property. This is at least another way, and this is how you can come up with another algorithm. This one's a little bit trickier, so I want to show you where this cut comes from. So let's go through the same kind of process as before. Now, you'll notice that the way I always am maintaining this blob in prim's algorithm, keep in mind I haven't given you the formal description of what prim is. I just gave you how it works and a way to convince yourself of its correctness. You might ask, okay, so that seems rather natural for the cut property. Like just because the cut is rather blatant for where it comes from. How exactly do you make sure you end up with a minimum spanning tree at the end? Well, one, the cut property tells me it's going to be all the edges I pick are part of some minimum spanning tree, right? The other thing is, notice I'm never creating a cycle. Do you see that when I do this, whenever I pick an edge that crosses the cut, I'm not picking an edge that's going to go back into the cut, like onto the opposing side, right? It always goes from inside to outside. It doesn't go inside to inside. So you know you're not going to end up with a cycle. So you'll notice that another way you can think about picking this least weight edge is just to globally pick the least weight edge. Does everybody see that? So for example, I could just pick this edge and say, hey, look, that edge should belong to some minimum spanning tree, right? It's the least weight of all of the edges. That's one thing you might say first up. However, you might say, okay, well, if I keep doing this, like suppose that this had an edge weight of 1, you might be compelled to pick that one, and then this one, and then this one. And you end up with a cycle. We need some mechanism to just prevent us from creating a cycle. Prim's had a very natural one for how the way the cut works and how you pick the edge that always crosses the cut, right? Why don't we try to use that idea here? So I'm going to augment this with another idea, where what we're going to do is instead of having one seed, we're going to have seeds at every single one of the vertices. So they're each going to be what I'm going to refer to as a cluster. So this idea is going to be what we call Kruskal's algorithm. So Kruskal's algorithm goes into more detail about this, but I want to show you how the cut property comes, like it's used here to ensure correctness. So what you do is you start off with all of these clusters. So I like to think of this as growing minimum spanning trees from seeds in clusters. So you can think of each cluster as its own separate little connected component with respect to the subgraph on that what we would call the induced subgraph of those within the cluster. So what's going to happen is inside of each one of these, a minimum spanning tree is going to grow, and when we add enough edges, we end up with a minimum spanning tree. So we have a whole bunch of these smaller trees of least cost all within each one of these clusters. When we're done, we're going to keep merging these clusters together to end up with one big tree. Think of it like bubbles. Each one of these is going to have a little minimum spanning tree for itself in there. Now, there's two problems. One, I need to make sure there's no cycles. So what I'm going to do is I'm going to use the same idea I just talked about. I'm only going to add an edge that crosses from one of these clusters to another cluster, never to the same cluster within itself. Same idea. So very often when you actually think about this, what we're actually trying to do is we're trying to make sure that we never pick an edge where they belong to the same cluster. The data structure you can use to maintain this is what we call disjoint set data structure, or some people call union find data structure. I'm not going to talk so much about that here right now, but that is the key ingredient to maintain these clusters. The other one is naturally always picking a least weight edge, such that you always make that edge so you add it to part of your tree to merge two clusters together. You use sorting. So all you're going to do is you'd sort edges, least to most, so ascending order by weight, Then you add least weight. Add next least weight edge between two clusters to merge them. So that's how this is going to work. You sort first the edges. Now, I'm not going to go into too much detail about how specifically that is done here. I mostly want to talk about the cut property. So notice that if I pick a least weight edge, and the edge goes from one cluster to another cluster, which we maintain with these disjoint sets, whenever I pick the next least weight edge, if it crosses from one cluster to another, we can guarantee there's no cycle, right? So, for example, if I include this one, what I can do is I can pick this one, and then I merge these two, right? Likewise, I pick the next least weight edge. Well, notice that I have a 1 here. So far we're doing okay. This is a pretty nice simple instance. So I could include this one. Notice I go from inside to another cluster, never within itself, okay? So you can keep doing this process over and over again by merging the clusters. So now notice that I only have 1, 2, 3, 4 clusters left. So notice that when I'm done, I've added enough edges such that it's only one big cluster. And inside that cluster is going to be a minimum spanning tree. Now, you might ask, Dan, how do you know it's a minimum spanning tree? Now, you can prove this with mathematical induction, but the key ingredient is how you pick the cut. So the cut is a little bit more subtle here. So notice here that when I picked and merged these two clusters into one and picked this edge, well, notice here, I did that because I had least weight and there were two separate clusters, right? There are two separate ones. Well, think about it. Let's consider the next edge we'd put in here. Well, we have one cluster here of vertices, and whenever we add a least weight edge, it is the next least weight edge. It goes from one cluster to some other cluster. So what's the one cluster we currently have? You have these 3 vertices. What if this is V1? It doesn't matter if this is V1 or V2, it's just one of the two. And everything else outside of this cluster is V2. So everything else is out here is V2. How do I merge two clusters? I always pick a least weight edge. Specifically, the least weight edge that separates one cluster from another, right? And that's actually how you pick the cut. So this is actually the cut property put into the setting of Kruskal's algorithm. This is the key idea that makes Kruskal's algorithm correct. Is that whenever I pick the cut, it's always going to be the one that merges to the clusters. And one of the clusters, it matters, the cut is going to be from one cluster to some other cluster, okay? So that's how you can use or see how the cut property pops up in 2 different algorithms that are commonly used to solve the minimum spanning tree problem. In fact, if you keep repeatedly doing this process, just like I did with prim, you'd end up with a minimum spanning tree.